Okay, I'm going to summarize how you translate what we know in the abstract basis into the position basis. So the abstract basis of states going to the position basis, anything that deals with the state psi, we now deal with the wave function, which is a function of x. This is the probability amplitude, remember, of finding the particle in the at a particular position x. Okay. Any energy eigenstates can also be, obviously any state can be written in the position basis. So the energy eigenstates I'll usually refer to as phi e I. Okay, and this will be a function of x. And we're going to see some specific examples of these in a minute. And the position eigenstates we've seen become Dirac delta functions, which we should use with caution. We're generally not going to pull these out of our bag, but we should know what they are. In the abstract basis, to find the probability of measuring a particular eigenvalue of an observable, you take the square modulus of the eigenstate with the state we're measuring squared. Okay, in position basis, what we do is we calculate the probability of measuring x between two particular points, xa and xb, and that's the integral between xa and xb of psi star x psi x dx. Okay, which is also equal to the integral from xa to xb of rho x, because this is just the definition of the probability density. Any inner product that we did in the abstract state, we've been doing by taking our row vectors and column vectors corresponding to these states and doing the inner product just the way we do ordinary vectors. In our continuous basis, we no longer do that. What we do is we take the integral over all space of phi star of x times psi of x dx. So we integrate the complex conjugate of one times the other over x. Okay. The expectation value of any operator O in the position basis is equal to the integral over all space of psi star times that operator acting on psi dx. I'm suppressing the psi of x bit, the argument bit here. So, for example, we've already seen that the expectation value of x is the integral from minus infinity to infinity of psi star x psi dx, which is just the integral from minus infinity to infinity of x times psi star psi. The expectation value of momentum is equal to, again, we sandwich the momentum operator, which is minus ih bar d by dx. Minus ih bar is a constant. The operator goes in the middle. It's a d by dx. It's a differential operator, so that differentiates everything that's on the right-hand side of it, which will happen to be this wave function here. Okay, so you take the complex conjugate of the wave function and multiply by the derivative of the wave function with respect to x, and you integrate that over x from minus infinity to infinity. Okay, now the time-dependent Schrödinger equation was h operating on psi is equal to I h bar d psi by dt. This becomes in the position basis, the Hamiltonian operator we saw was minus h bar squared over 2m d2 by dx squared plus v of x. So, and this is operating now on the wave function psi, and this is equal to I h bar d psi by dt. And psi in this case is, we're dealing with a time-dependent Schrödinger equation, so our state is fully time-dependent, which means we need partial derivatives here and here. Okay. Now, if you know the wave function at a particular point in time, how do you know what it is? How do you get the full time dependence of that state? Well, we've seen how to do this in the discrete basis. What we do is we write it as a linear combination of energy eigenfunctions, first of all. So what we do is psi of x is equal to the sum over I of AI times the energy eigenfunctions in the position basis, right? This is just, what this is just this, where we've made the translation of psi becomes psi of x, and the eigenstate EI becomes psi EI of x, right? So we've just replaced these abstract states with their versions in the position basis, okay? If you then want to know what it is at any time in the future, all you do is you multiply each coefficient by e to the minus I EIT over h bar times psi EI of x. Okay, so this is exactly what we've been doing before. Nothing has changed. How do you know what these coefficients AI are if we don't know? Well, remember, these are just the result of taking the inner product of psi with EI. Okay, what does that mean in the position basis? Well, we know how to translate inner products into the position basis. They become integrals of the two states. So this is the integral of EI becomes psi EI of x star, because it's the bra version, and psi becomes psi of x dx. Okay, so this is how you go back and forth between, or this is how you find the coefficients here. Okay, by the way, this is essentially just a Fourier series, right? This is a Fourier series expanding a function as a linear combination of other functions. And we know in Fourier series that the coefficients are the integrals of these functions with this particular function here. So it allows you to find the coefficients that relate these two functions together. If you then substitute this back into the time-dependent Schrödinger equation here, what you end up with is the energy eigenvalue equation, which says that minus h bar squared over 2m. And now we've got rid of the the time dependence. We've just got these energy eigenfunctions, psi of x, plus v of x times phi EI of x. That is equal to EI phi EI of x. Okay, now you can verify yourself that this is what you get if you substitute this into the time-dependent Schrödinger equation. Right, so this here is the energy eigenvalue equation. So this is how you find the energy eigenstates in the position basis. It's no longer a matrix equation, which is how we've seen the eigenvalue equations for operators previously. It is a differential equation. It is a second-order differential equation that you have to solve. Okay. That is basically how you go back and forth between the two bases.